Good afternoon. This is Keegan Sawyer. Luke, are you on? Are you able to hear me?
You must be on mute.
Let's try this again. Dr. Alphey, are you on the line? We had you muted and now unmuted you. Unmute him.
Oh, okay.
Can you hear me?
Yes, we can. Great.
Very good.
So I'm going to give you the right.
So we're passing the computer rights over to you now.
Okay.
Change it forward.
How's that?
It looks great. Thank you. So we'll just start in a couple of minutes. There's a few more people joining us on the line.
I cannot see it on the.
Good afternoon, everyone who is joining us for today's webinar. Some considerations for the potential commercial applications of gene drives. If you are just joining the line or just recently joined, please be sure to mute yourself on the phone so that we do not have static and feedback. I did hear some lovely classical music a moment ago, so please make sure you are on mute. So thank you, everyone. This is she.
Okay, thanks.
Welcome, Stephen. So this is Keegan Sawyer. I'm the director of the National Academy of Sciences, Engineering, and Medicine study on gene drives in non-human organisms, recommendations for responsible conduct. Today we have a webinar with Dr. Luke Alphey at the Pirbright Institute, who's going to be sharing some of his perspectives and experiences from developing the Oxytec, and I'm going to let him give a better introduction of himself than I will. He will be speaking with the committee for, I guess, the first half an hour of this webinar, after which members of the committee will be asking Dr. Alphey some questions. All members of the public are invited, of course, to listen to his talk and the Q&A session, but we will not be taking questions from members of the public during this webinar. So Dr. Alphey, if you are ready, you can begin.
All right, thank you, Keegan, and thanks for inviting me. So I'm Luke Alphey. I'm a research group leader at the Pirbright Institute, which is a public sector virology institute in the UK. I'm also a visiting professor at the University of Oxford. I also was the founder and for more than 10 years the research director of Oxytec, which is a private sector company in the UK, recently acquired by Intrexon, that built a business around the use of genetically modified insects. And I should say that I don't represent any of those institutions that I've mentioned or any others that I might be associated with, and certainly not in this presentation, which is entirely my own views, though I'm not speaking for any of those organizations. So my brief was to say a few things about various aspects of commercialization of gene drive systems and in relation to Oxytec, which of course was not developing a gene drive system, but these were the questions that I was asked to address. So I'll go through, say a few words about each of those things over the next 20-30 minutes, and then and perhaps we will have some sort of discussion from there. So just to introduce Oxytec for those of you who don't know, and I know that some of you are quite familiar with it. I was an academic researcher at the University of Oxford and developed some potential applied uses of genetically modified insects while I was there from my background in Drosophila. And we founded the company in 2002. I'll say a little bit more about timelines later. So it was a spin out from the University of Oxford, a for-profit company with relatively conventional risk capital investment. And it was recently acquired. Oh, sorry, this slide is wrong. It says acquired by Intrexon in September 2014. That should be 2015. So only a matter of weeks ago. And at that point, it had about 50 full-time equivalent staff. The funding, as I said, was relatively conventional risk capital from for-profit investors, and then also some project or other types of funding from government and philanthropic sources. And although a relatively small company, we collaborated very widely internationally, and particularly in areas where we might actually be using these modified insects, such as with the US Department of Agriculture, Malaysian and Brazilian and Cayman Islands entities, and also with collaborators, academic collaborators, to help develop the strains or undertake various experiments that they were better suited to do than we were, and so on. And the aim, of course, was to control pest insects, and that was both in agriculture and in public health, although the public health aspects are perhaps perhaps better known, but certainly from the beginning focusing on agricultural pest insects, so direct feeding pests, but potentially also disease vectors, although in practice more direct feeding pests for the agricultural side, and then also in public health, mosquitoes, and particularly dengue and its principal vector, Aedes aegypti. And the aim was to use genetic methods to provide what everybody would like, which is safe, sustainable, economic methods for controlling some of these major harmful pests in these various sectors. Okay, so to go back to the expressed questions, and I should say I am, although I primarily a research scientist, and I have started a company and directed it for some time, but that's just one, which does not make me a business school expert or economic expert or whatever. So these are just comments on, extrapolation from a single data point, which, as we all know, is not necessarily reliable. However, what would be sort of general business considerations? I think the first question, yeah. So I think for Oxitec, it was clear from the outset, from the sort of original idea, that potential use of engineered sterile insects was potentially beneficial, and there are some particular attractions that are shared with genetic methods more broadly, and one of them is the species specificity. At least in insects have what you might call relatively clean species, so that males of one species will mate only with females of the same species. You can find species complexes and so on, but broadly, fertile hybrids from cross-species mating is really unusual. So that specificity built into the method. So if the control agent that you're releasing is some sort of modified insect, then the fact that it will only directly interact with and therefore pass on its sort of genetic cargo, whatever that is, to other species, to other insects of the same species, minimizes the direct off-target effect of the intervention compared with most other interventions you might think of, and the sort of baseline for this is obviously chemical insecticides, which would rarely have such species specificity. And another aspect is that, again, perhaps unlike chemicals, the control agent, your modified insect, let's say male insects, will go out and look for the wild pest insects for you. So their natural self-dispersing and mating behavior means they will go and look for the target for you, which again is a relatively unusual feature compared with other control methods. A big factor, I think, that was extremely helpful in the genesis and development of Oxitec was the large-scale use of, the potential use of these insects, even before we made them, was remarkably well understood by analogy with conventional, which is a sterile insect technique, which is to say the use of radiation-sterilized insects. So, of course, the method, the genetic basis of the sterility is rather different between irradiation and the sorts of genetic engineering that we were doing, but what you do with them once you've made them was really rather similar. And so a lot of the mass rearing, potential for deployment, resistance, the numbers you'd need, how you rear them, a lot of the economics and so on, was all pretty well understood. And that was extremely helpful, not just from a technical perspective in terms of doing it, but from an economic and in the sense that the risks of deployment were much lower because of that precedent from radiation-based SIT, and investors certainly understood that if we could make these strains and if we get the permits and public acceptance to use them, then we had a pretty good idea of how we would use them based on these precedents, and that was very helpful. Another key aspect, which I'll touch on customers and so on later, probably several times, was the early interest of the US Department of Agriculture. So shortly after we published the initial paper in 2000, the pink bollworm program, which is one of the large radiation-based SIT programs run by the United States Department of Agriculture, contacted us, two particular individuals program had seen the potential of this method, even though we had only this partial demonstration in Drosophila at that time, and were very interested to work with us. And that, third-party and customer-type validation was, again, pretty influential at all steps of developing the program in terms of attracting finance and so on. Something that looks like a customer is obviously very attractive from a business point of view. Okay, and in terms of the sort of more negative aspects, so issues or features that made it a little harder, perhaps, the flip side of the species specificity, which I think is very attractive.
Dr. Alphey, I'm not sure if you can hear me, we've lost sound.
Oh, correct. This is not.
Give us one moment. It looks like Dr. Alphey's phone line has disconnected, and we are going to try and reconnect him in just a few minutes. Please bear with us. For those of you who have just maybe recently joined the webinar, we are having an audio connection difficulty, and we are working to resolve it in just another minute, so please bear with us. Dr. Alphey, can you still hear me? Oh, it hung up on us. Okay. Give me one more moment. We will attempt that again.
Try. I could hear you typing.
Dr. Alphey, can you hear us?
Can you hear me?
Yes, we've got you back again. Alrighty, we're going to pass presentation rights back to you again. Apologies, everybody who has joined us for today's webinar.
Probably. You can still hear me?
Yes, perfectly.
Good. Okay. Can you tell me how far I had got at the point you couldn't hear me?
Yes, we're going to pass presentation rights back to you. You were just getting into discussion of some of the considerations for commercial applications. So you're talking about organism specificity and early interest of the USDA.
Okay.
So we've passed the rights back to you, and you will need to share your screen.
Okay, can you see that?
Yes.
Good. All right, sorry about it, probably a bit of repetition, but I'll I'll start from early on this slide then. So I think you probably did hear me point out that it looked like an attractive technology. It had some particular characteristics, species specificity, and with potential environmental benefits associated with that, and the sort of self-dispersing nature of the control agent that were a little unusual relative to methods and clearly potentially beneficial. Obviously, in terms of species targets, we were looking at species that were not well controlled by other existing methods, because any kind of control method will exist in a world where there are insecticides and GM crops and environmental controls and a whole bunch of other potentially competing or complementary methods. Okay. And so a key feature, I think, a very helpful feature in terms of everybody seeing where they were going, and so reducing at least technical risks, was the well understood 50-year history of the use of conventional radiation sterilized insects. And then associated with that, customers are also crucial in the early interest of the U.S. Department of Agriculture. The pink bollworm program, so phylogenetically rather distantly related from Drosophila, which was the model organism in our original paper published in 2000. Nonetheless, a couple of people from that program, particularly Bob Staten and Tom Miller, saw the potential and contacted me really right after we published that paper. And that external interest and potential customer interest was quite influential with everybody, investors and potential funders and early stage funders and so on, in terms of helping persuade everybody that there was a business here if we could get through all the obstacles. In terms of issues, the species-specific nature, which I think is very attractive from an environmental point of view, also inevitably limits the market size for each product, so each one will only be for a single species product. And it also limits the potential applicability, so if you were a farmer and your crop was being eaten by a dozen different pest insects, you might prefer something a bit more broad spectrum than a dozen different species-specific interventions. But nonetheless, there are still plenty of cases where there are single dominant pests that are not readily controlled by current methods, and so there's a clear customer need out there that you could define that might be met by a product of this category. One of the big issues all the way through has been, particularly at the outset, has been the regulatory and public acceptance uncertainties, and I would say, from a regulatory point of view, that is not just the potentially high cost of getting through regulation, but the uncertainty around that is very difficult for financial investors to deal with. So the uncertain timescales there, I think, were particularly had a particularly negative impact on our ability to attract finance, get a good valuation for the company, and so on at the outset. And also limited commercial precedents, although there's plenty of precedent for sterile insect methods, use of radiation sterilized insects, the large programs, large SIT programs are mostly government run and therefore are actually relatively little commercial precedent. And sort of similar to that, with a relatively new technology, it was not obvious that we could license, and we were not able to license the technology to an existing commercial entity in the way that you might aim to do if you came up with a new drug or potential drug or vaccine or something like that. Okay. So, then a key question in terms of business model is what are you going to sell and to whom are you going to sell it? And there are a number of, there's a spectrum of possibilities, by no means mutually exclusive, that we addressed at Oxtec. One would be what you might call almost the sort of IP only, intellectual property only kind of sale. So we would develop and sell the technology. So you could imagine with an existing radiation-based sterile insect program, if we could provide them with a better strain that did broadly what they were doing already, then they might only want the strain, and they themselves would be experts in rearing and distributing the insects. And so essentially, it would be an intellectual property sale of the technology embedded in some genetic technology embedded in some insects. Or you could potentially sell engineered insects. So if you imagine let's say a mosquito control organization that was used to having people go around and spraying, and it was used to doing its own monitoring and so on, you could perhaps provide engineered insects that they would distribute in much the same way as they had been using chemical sprays and inspected searching for breeding sites, but they would do the rest rest of the monitoring and so on themselves. Or you could imagine a full service situation where you go to somebody who wants control of Aedes aegypti or control of a particular plant pest or whatever, and you provide that full service based around the use of GM insects, but including other components such as monitoring and so on. What we were not really building the company to do, which is not to say that we wouldn't do it under the right circumstances, was sort of fee-for-service research contracts where people wanted a particular thing made or a particular strain or something like that, and they wanted someone to make it and would offer a research contract to do that. So that really was not the business model for Oxitec. And in terms of how did the business model evolve, actually perhaps rather unusually for a startup or a biotech startup, more than 10 years on, we were still doing what we set out to do, what we said we'd do at the beginning. But really the only significant change in the business model was perhaps the increased provenance of mosquitoes and public health, particularly Aedes aegypti, relative to agricultural pests. I would say when we started the company in 2002, it was really primarily focused on agricultural pests, although with mosquitoes as well. And the mosquitoes just went a little faster, and I would say that was, and therefore sort of increased in prominence in the portfolio. And that was partly because of the advocacy of Bill Gates and others around mosquito-borne disease led to more focus on mosquito-borne disease, and also the increase over the period in the wealth and development status and so on in dengue endemic countries made it much easier to persuade financial investors that there might potentially be some sort of return from a dengue control solution, and also I think probably the increased wealth and development in those countries leads people in those countries to push for something to be done about dengue, and so considerably more demand or technology pull for any innovative solution to these problems than perhaps there was around about 2000 or so when we were thinking about commercializing this technology. Okay, what sort of things would you look at? Well, I'm sure you run a whole business school course on this kind of thing, just very briefly. So that first quote, identifying, anticipating, and satisfying customer needs profitably is actually a definition of marketing from the Chartered Institute of Marketing, but it could pretty much be a definition of business, or at least for, I put profitably in brackets, which they did not, because there are not-for-profit businesses and other ways to establish organizations. And part of that is anticipating customer needs. So my second quote, attributed to Henry Ford, who may or may not have said it, if I'd asked people what they wanted, they'd have said faster horses. Particularly with new technology, you may need to think about what the customer needs are and ways of satisfying them that the customer themselves may not originally have anticipated. I think that would probably apply to most genetic technology today. Certainly these sorts of applications, gene drives or sterile insects or whatever. And you need a customer, and you need them to be able and willing to pay for whatever it is you're developing. Pay on a for-profit basis or a non-profit basis or whatever, but somebody's got to be able to development and so on will cost money, the technical development, but certainly the regulatory costs and so on, and communication and so on will have a significant cost associated with them. And on a for-profit investment basis, you need to be able to recoup those costs, and preferably with some profit, and something to recognize the risks that the cash investors are taking by putting up their money early on for an uncertain outcome. So who is the customer, and what are you selling? I touched on a previous slide, at least for Oxitec. And then if the development costs are high, which I think if you take into account not just the technical development costs, but the regulatory costs of getting your product through to the ability to sell it, those sort of aggregate development costs, then you're unlikely to be able to make your money back from a single sale in a conventional commercial way, but rather you spread those development costs over multiple sales. And clearly for sterile insects, where you can treat different populations and so on in different places, there is the possibility, first of all, for selling to multiple customers, and then also for some sort of ongoing business of ongoing use of the sterile insects, and so repeat sales seem pretty feasible. And I think that is probably one of the questions, one of the issues behind these questions about commercial model for gene drive, is that if you think about a aggressive single-release kind of gene drive, those questions with repeat cells are harder to see. I'll come on to that a little more later. In terms of timescale, as I mentioned before, people recognize that of course you need permits and there'll be some burden to them, but for a new technology, the uncertainty over what you have to do and how long it will take and what it will cost, but particularly how long it will take. So time is money for a financial investor, and they want a return on a particular timescale. Very often funds are structured to have particular timescales built into them. And if you can't say how long it will take to get through the regulatory process, then that's going to make it very difficult for many classes of investors to invest. So to continue on that, timescale is an issue. And I would say the majority view at the time when we started Oxtec was that there wouldn't be any field usage in it's commercial otherwise, or at least if there were, then it would be on at least a 10 or 15 year timescale from 2002, I suppose, when we started the company. I would say that view turned out to be overly pessimistic. And so we were able to move faster than that, which in this particular instance you could say was a sort of role of industry in driving innovation and through sort of developing these things, then driving regulatory processes. So just to sort of look at a timescale, the first line is publication dates for the first genetic transformation. So the first demonstrates the ability to put any kind of foreign DNA into the genome of various insects. Drosophila by far the earliest in 1982. Medfly, which happened put in 1995. Aedes aegypti, so the first mosquito in 98, and then the first moth, Ebola, and silk moth both published in 2000. Now, relative to these, 95, 98, 2000, first dates of any kind of foreign DNA into these pest species. So I counted the original sort of concept for engineered sterile insects in 94, as you can see, actually before we could put the DNA in. Patented the idea with some basic Drosophila, some demonstrations, patented the idea in 99, published in 2000, found Oxtec 2002. Just a word on patents, I have it in this timeline here. The ability to patent is absolutely crucial for attracting private sector investment or financial for-profit kind of investment. If you don't have, so the patent deal is disclosure for a limited term monopoly over use. If you don't have that, then if you as the first entrant into the field spend time developing the technology, first time out it's likely to be slower and cost more and more false avenues to go down, which you'll need to explore, and then get through the regulatory process. And again, first time out it's likely to be more expensive and so on. If another entity can just come in right behind you and copy that work, avoiding the costs of going down the false avenues and now with some regulatory precedent, then inevitably they will be able to undercut you. Their development costs will be lower, and you won't be able to compete with them. And so, from an investment point of view, if you're an investor, why would you put your money into something like that? And so, a secure intellectual property foundation was absolutely crucial for attracting investment I would say, for Oxitec, but also for biotechnology more generally. Okay, and then relative to those sort of timelines, transformation up here, in terms of actual field use, so we had actually, I've left off all the development work, the regulatory side, and case trials and so on, but actual open field release, first was 2006 in Arizona, a pink bollworm in collaboration with the U.S. Department, these were all Oxitec, but in collaboration in that case with the U.S. Department of Agriculture, and then Aedes aegypti mosquito, first in the Cayman Islands, and then Malaysia, Brazil, and more recently, Panama. So I think to go from the first ever transformation being published in 2000 to field release in 2006, or even the slightly more extended Aedes aegypti timescales, 98 to 2009, perhaps I should say we made our first transgenic Aedes aegypti in 2002. It is, reasonably rapid progress. So although it's absolutely incremental, cautious, step-by-step process, so I think the view that it was going to take a very long time, sort of decadal, multi-decade timescales, turned out to be overly pessimistic. And in this case, that was driven by industry in the sense that I was doing this from an industrial context. But I don't think that was sort of inherently or necessarily so. I'm not sure that there are any particular factors there apart from the ability to engage in the long term that made it specifically commercial or industrial or private sector issue that could not have been done from another sector. I do think that regulatory and public consideration is aided, stimulated by having at least one, and preferably more than one, relatively near-term tangible cases around which to focus consideration. And if you don't do that, then you don't really have anything to get a handle on. So if you say, well, this strain in this place for this reason, that's one thing. But if you want to say, we want to use genetically modified insects to control stuff, how about it? Then optimists can very easily construct utopian visions of clean, safe, efficient, cheap, whatever, control, minimal environmental effects, and so on. But pessimists equally can construct sort of dystopian scenarios rather easily, and neither of these two probably have that much grounding or with reality, and I think that tends to be pretty unhelpful. It's also quite hard to get the attention even of naturally rather busy regulatory agencies for hypotheticals, and just being able to engage in a meaningful conversation is very helpful if you have some sort of case on the table for them to consider. And and you need a bunch of other things. You need drive and passion and funding and donation and so on, and these are all important, but they're certainly not specifically private sector qualities. Yeah, in terms of the next question I was provided with in the brief of lessons learned, if you like, I think the species-specific aspect has always been attractive from an environmental point of view, but it reduces the market size. And there's a number of issues about market size. I think many of the most desirable applications are for areas that are not big commercial targets, that are pests of specialist crops, or, and therefore somewhat niche markets, particularly high-value horticulture and so on, or in public health where there's not traditionally been a great deal of money available. Conservation biology even, which perhaps has even less money. And if you have relatively limited market sizes and product by product or even event by event regulation, then what would be attractive targets from any kind of technical, environmental, risk analysis or whatever perspective are actually frozen out by the costs associated with those regulatory burdens, timescales and uncertainty and so on as well certainly, but actually just straight cost. And the uncertainty, then an even bigger question, if you don't know how long it's going to take, whatever, do you really want to set down that path, or are you going to be stuck in some quagmire, more or less forever, or at least until you run out of money? And the high regulatory hurdles put technology in general, biotechnology in general, you can see this in other areas, but certainly be true here, and control of the technology under the exclusively to hand that control to organizations that have deep enough pockets to do that. In the commercial sector, that really means larger multinational companies, where in many cases you might prefer more university, small company, and so on, players to be able to operate. If the regulatory hurdles are too high, they simply will not be able to enter or survive in such markets or in arenas. So now to the last, but perhaps longest question: do gene drives have any potential commercial applications? Well, of course they do. I have started one sort of company, but a lot of interesting developments are driven by entrepreneurs with novel business models. And I'm certainly not an expert in that area, but here are some sort of considerations, if you like. I think on the sort of fee-for-service area, so if a large entity, whether it's government or philanthropic or whatever, wanted to build gene drive applications, there are a number of things that might be subcontracted to the private sector. But I think probably the question was really focused on the potential for building a business based on creating and selling modified gene drives. And so I'll briefly, because the problems earlier, we're probably running a little short of time, but I'll think very briefly about three potential applications that vary by the invasiveness, if you like. So the first one would be a strong molecular drive driving a lethal or sterile gene. And even though it's a strong drive system within the insect, so that it's like it's passed on the genes at near 100% efficiency, such a system is not expected to spread. It is effectively a more efficient sterile insect system. And we considered the use of such a system, at least very briefly, now back in the original engineered sterile insect paper back in 2000. And you can easily imagine a commercial model built on those, much the same way as we did for Oxtec, similar sort of considerations. The gene construct's persistence time in the environment would be greater, which would have some regulatory effects, but it wouldn't invade an entire species, and it might be more efficient in its applications than sterile systems without such a drive. Okay. So a second case, at the sort of other end of the invasiveness spectrum, think a highly invasive gene drive system, which has had quite a bit of press recently. So I'm thinking particularly of some nuclease-based designs that Austin Burt described from 2003 or so onwards. It originally described in the context of hooking into nuclease genes, but obviously now perhaps adapted to other nucleases, particularly CRISPR-Cas9 nucleases, and a couple of the designs just mentioned there. These systems are expected to spread through an entire species, or perhaps a species complex, if they can form fertile hybrids. And one potential outcome would be extinction of those target species. That may or may not come to pass, depending on various criteria, but that's certainly a potential outcome. And for me, and perhaps this just shows my lack of imagination, but it's hard to see a sustainable business model there. I'm not sure that there are very many species where we would want such a drastic intervention. If we were talking about a species extinction, we have only driven 2 species to extinction, if you like, and that's smallpox and rinderpest viruses. And to do that even with a mosquito is quite a step from there. I just doubt that there are very many separate species targets where that would be considered appropriate, if it were at all. And again, go back to the analogy that we could draw with classical SIT. You can think about classical biological control, the introduction of a predator or parasitoid where you expect it to establish and maintain itself indefinitely. And that is not usually done on a commercial basis, unlike augmented biocontrol, where you expect continued, periodic or additional releases, for which there are very many commercial companies with various species targets. I think the regulatory and public issues around species-wide permanent intervention, and I appreciate there may be some ways to reverse some of these drives under some circumstances, although whether scientists, regulators, and public would consider them reliable is another question. And so the uncertainties around regulatory timescales, again, as well as costs, I think probably will be larger than they were for engineered sterile insects. On the plus side, of course, any further genetic method aimed at insects, it is building on some precedent now of the use of the engineered sterile insects, which would probably be helpful from a competent regulatory perspective. And again, there may be areas within such a program where there might be private sector involvement might be key, but it seems to me more likely that such programs would be driven by governmental or philanthropic agencies. And the examples that I gave were aimed at population suppression, but of course there'd be somewhat similar issues for replacement, so driving a reduced vector competence gene through target population. And then the final case that I just want to consider briefly is intermediate between the two. So it's a gene drive system that's expected to spread, but only locally, so through a target population, but not the entire species. The only way I know, the only sort of designs that I know to have this sort of effect are based on dominance, so there may be other ones. And such systems are expected to spread through local populations and colonize them, and definitely in those, but not to invade adjacent, moderately isolated populations. There, I think it's easier to see a sustainable business model, and indeed a much wider range of targets. I think there may be many species for which we'd like to affect or in some way or treat one target population, but not other target populations of the same species. Perhaps one where it's invasive, or one where it's native, or whatever. And then each such population is potentially a different target, and potentially multiple customers, some sort of maintenance for the strain out post-release. And also the regulatory situation. If it's a relatively localized population, legislation, it probably has a single regulatory agency, whereas I think the transnational aspect of more invasive species-wide interventions provides a further difficulty and uncertainty that would be further difficulty for a private sector entity, or indeed anyone else, but would be a problem for a commercial application. So I think I will stop there. I should, of course, as with all these things, thank everybody involved in the whole project from start to finishing, and this is just a subset of the major funding agencies and collaborators that we dealt with. Thank you.
Thank you so very much, Dr. Alphey, for that informative presentation. Now we've entered the time for some questions from the members of the Committee on Gene Drive Research in Non-Human Organisms. So we are unmuting some of you, but please check to see if you are unmuted so that you can ask Dr. Alphey some questions. And Dr. Alphey, do you have maybe 20, 25 minutes, even though we had a little glitch in the middle?
Sure.
Hang with us? Okay, excellent. So if any members of the committee have a question, please say your name and ask your question now.
So this is Wayne Landis. Can you hear me okay?
I can hear you fine, thank you.
So my question is regarding the liability and insurance demands for something like a gene drive that people are thinking about putting into the wider environment, especially non-target effects, off-target effects, potential effects to other systems. I mean, in a business, you'd think there'd be some liability insurance and some liability requirements based on probabilities and risks. How's that been done in the past?
Okay, so product liability insurance is reasonably well understood. I think for the more persistent interventions, that might be a little more problematic. It's certainly been talked about since the early GM insects and for other interventions as well, but has not in fact proved to be a big showstopper.
Hi,
Any other questions? Okay, great.
Yes, Dr. Alphey, this is Jason Delborn from North Carolina State University. My question is, given the difficulty of monetizing some of the possible pathways for gene drive, do you think that we face a risk that the development of the technology will be biased towards the kinds of forms that can be monetized, and we might miss out on more efficient or more effective ways to use gene drive as a technology, but not pursue those pathways because they can't be commercialized and they can't attract the right kind of investment? And if you think that is a risk, how do you think we might be able to overcome that? Thank you.
So I'm not quite sure which way around you had the risk there, but I think there's a problem, as I alluded to, that the regulatory hurdles, so the cost, not so much of developing the strains, but of getting them into use, will freeze out small entities from doing it. And so, whether that's on a commercial basis, so small companies, or on a, perhaps not-for-profit or academic basis, so universities and research organizations and so on, I think that perhaps only the people with deep pockets, so, big philanthropies, governments, big commercial companies, will be able to get a product through to large-scale use. And that's true even if large-scale use, for a species-wide intervention might mean just, a few seeding insects. It's not actually the scale of doing it, but I think only people who put up a lot of money are going to be able to play the game. And so what might be valuable niche applications, I think, will struggle to benefit. And you certainly see that in other sectors. You just look at GM crops, and they're largely the big broadacre varieties where there's potentially very large commercial return from from a normal trait, and it's been very much harder to apply basically equally beneficial technology to smaller and more specialized crops, even though some of the problems that might be solved by those sorts of technologies are possibly more pressing for those particular crops.
Any other questions?
Oh, hi, Keegan. This is Lisa Tannehill. I had a quick question for Luke before we sign off. So I was just, that's okay. So I was just curious if you or any of your colleagues know how many companies are currently out there that are doing this type of work with the aim to take this to field deployment.
Well, I'm not. So the only company that's ever released any GM insects or even said that they want to is Oxitec.
Mm.
I'm not aware of any companies developing gene drive systems for commercial applications, or that are sort of publicly said they are. If they were doing it in situations, I work on insects, and so applications in other areas, it's possible that I wouldn't know about, but I don't know of any. So I think actually, commercial involvement in this whole area has pretty much been Oxitec so far, and particularly with gene drives, I think because of the difficulties in business models and uncertainty over regulatory public acceptance issues particularly, and the sort of issues I talked about, development of gene drive systems, at least in insects, has been overwhelmingly driven by large philanthropic agencies primarily, but government or not-for-profit funding.
This is Joyce Tate here. Can you hear me?
Yes,
Hello?
I can.
You can, yeah.
I wasn't sure. You, yes.
I was trying to mute myself. I'm interested in the kinds of business models that might succeed in this area, and I think what you've said today is kind of consistent with my thinking too, that I can't envisage it being the kind of area where people are desperate to leap onto this great new way of making money. I think it's going to be very difficult to get commercial activity going in this area for a whole variety of reasons. And I kind of wonder whether the approach you were developing in Oxitec is something that actually, A, does provide a viable business model for a company, even a small one, and B, actually allows us to learn useful lessons that could help us to develop gene drives in the longer term if we only take the time to develop those lessons. So the question is one about the speed with which we should be trying to find commercial applications of gene drives, whether it's better to hold off on that for a while and learn the lessons we can for the kind of more targeted approach that you were undertaking in Oxitec.
Okay, thanks. I think the key for me is this sort of step-by-step approach. I think that's absolutely crucial for regulatory and public confidence, and indeed confidence in the scientists that they, know and understand the technology. So for me, I would like to see a development path that starts perhaps with strongly self-limiting systems like Oxitec's engineered sterile insects. Well, that's great because that is where we started, and so we, to some extent, we've taken that first step. And then within each of these steps, progressively small-scale trials and larger use, which is again certainly what Oxitec has been doing. Perhaps a little harder to see how you do that with the highly invasive gene drive systems, but they would be some way down the road, because I would prefer to see, what I had is case 1 and case 3. So a molecular drive that's not predicted to spread, and then not necessarily every step along this path, but then a drive system that is expected to broadly stay where you put it and is much more controllable and easily reversible and perhaps genuinely reversible than some of the highly invasive drive systems. And those used not necessarily in a for-profit context, although that would be fine too, but used so that scientists of all sorts and not just the synthetic biologists but the ecologists and the epidemiologists and economists and so on understand the properties of these systems and their failure modes and resistance and all these things that we will inevitably see to some extent or have the possibility of seeing. And learn each of those before we get to my mind, the more drastic and controversial and all those sorts of descriptors, species-wide interventions. And that's not to say that those aren't, valuable and desirable, at least against some targets. But I don't think that's necessarily where you'd want to start. Any more than you would in a space program or whatever. If what you really, really want to do is start a colony on Mars, you wouldn't, that's fine, but it's not the first thing you do.
Yeah. Thank you.
Any further questions for Dr. Alphey? Well, with that, thank you so very much for joining us today, Dr. Alphey. This was a great presentation and discussion. Our next webinar for this series will be Thursday, November 5th at 11 a.m. That webinar will focus on key principles and considerations for risk assessment of gene drive research and applications. All members of the public are invited to join us for that day, and you can register through the Gene Drive website. So thank you again. Until the next one.
Thank you, Rob.